if we consider energy per mole of the material, then I can write E is proportional to RT. R is the gas constant, T is the temperature, absolute temperature, and gas constant value is 8.314 into 10 raised to 7 ergs per degree per mole. Okay. This is a very standard equation, and you should remember it, even though it has not much relevance to our topic of discussion. Okay. So, the energy of the photon we should understand for our understanding only. The energy of the photon you should not be confused with the brightness or intensity of the source. The more energy, more intense, no, nothing like that, but it relates to the color of the light. Energy corresponds to the color of the light as far as visible range is concerned. What about ultraviolet rays? You may feel the ultraviolet rays, that also you will feel only the energy. You do not see the ultraviolet range, energy wave, electromagnetic radiation. Sometimes infrared, you can see the colors, but it looks like, as its name suggests, it looks like only red. So, other areas, no, you cannot see the colors. Sometimes ultraviolet substances which absorb ultraviolet rays radiation, they look a little bit yellow. So, from yellow to red you can see personally as a human being. I do not know about the animals what colors they perceive or something, but my understanding is most of the animals see they do not see visible colors. That is my understanding. I may be wrong also, because if you many animals will see the whole world only as if they are seeing a black and white photo. They will look dark shade or light shade, but they cannot see red color, green color, etc. So, if you are looking at a red color in a Spanish bull fight or something like that, the idea how it looks to that is you are holding something dark shaded material. You can as well use a black flag also. It does not make any difference to the bull. Okay. That is a difference. That apart, it is only my way of understanding how we perceive the colors. So, the intensity of the color is you can feel, you can see it. The power of a light source is given by P is equal to number of photons into multiplied by the energy of the photons. So, it is the energy of a beam of radiation that reaches a given area per second. This I think you can imagine. Take a torchlight and see the focus it on a wall opposite to you, and you will see, if you are very near, you will see a squarish area illuminated by the light, or roundish area depending upon the actual size of the actual shape of the torch. But it is what you can see, if you are farther away, the area that is illuminated will be bigger. So, that is understood, is not it? So, it is the energy of a beam of radiation that reaches a given area per second. If the given area is very far, the energy remains diffuse and you may not be able to see the illuminated area at all. If the energy is less, definitely you will see the illuminated area. So, the intensity of a source of radiation is the power emanating per unit solid angle. Okay. So, this is how we define scientifically. Now, this is again the electromagnetic radiation which I have explained to you earlier. but this is another way of representation. It is a very beautiful way of representation. This is from Clark's table I had taken earlier. So, now we have understood so far the properties of the electromagnetic radiation, correct. So, now what we will do for the next 1 or 2 hours is to understand how the electromagnetic radiation will interact with the materials, because any spectroscopic instrument will contain a radiation source. It will have the radiation source has to pass through prisms and then through vacuum, through the sample and then through the machine up to the onto the detector, etc. So, it has to interact with several types of materials. So, what are the effects of the interaction of the material on the nature of the electromagnetic radiation? So, to study that, let us look at the how the radiation is transmitted. Okay. So, the rate of propagation of the electromagnetic radiation through a transparent material, that is atoms, ions, molecules, particles, anything, liquids, okay, gases also we can include, that is less than that of a vacuum. What we are saying essentially is, in the vacuum, if the electromagnetic radiation passes, it passes across a given space at a particular speed. If it is vacuum at a particular speed, but if that vacuum is filled with ions, gases, molecules or liquid or solid or glass or plastic or anything, if we have to make them pass through, then the speed of the light would be, the rate of propagation would be slightly different inside that space matrix than in the vacuum. So, the frequency will not change, but it is only the speed that will change, and the frequency change will not be observed. It means that permanent energy transfer to the medium does not occur. Why? If part of the energy is absorbed by the material, then the total energy of the wavelength electromagnetic radiation should change. So, if the total energy changes, frequency should change, wavelength should change, but we do not see such things in the normal practice. Why? Because whenever radiation passes through a given matrix, for example, through a solution, in the solution its speed will be different, but outside the solution, when it comes out of the solution, again it has to, it passes at its own speed. That means, the energy is not passed down to the material whenever electromagnetic radiation passes through a given matter or matrix. Therefore, the interaction involved must be only temporary. That stands to reason, is not it? So, the what is that information, what is that temporary interaction? It is the interaction which is nothing but a little bit of deformation of the electron clouds, temporary again, and the moment they come out of the media, again the electromagnetic radiation regains its original energy or glory or whatever it is. Okay. So, the electronic clouds associated with the molecule, they get a little bit disturbed whenever the electromagnetic radiation passes through a given matrix containing atoms, molecules, electrons, etc., etc. So, I think all of you know that atoms, molecules, etc., they all contain electrons. So, what is the time frame? The electromagnetic radiation will interact with the matter. I have written it here in the slide. it varies from 10 raised to minus 14 to 10 raised to minus 15 seconds. Within that time, there is an interaction between the electromagnetic radiation and the matrix material, that is molecules, gases, ions, etc., etc. Since the velocity of the radiation in the media is wavelength dependent, the refractive index of the media also must change. This is one of the consequences of the electromagnetic radiation that passes through a material which does not absorb. If it absorbs, the consideration changes, but if it has to pass through and come out, then only the refractive index of the media changes rather than the electromagnetic radiation. So, the variation of refractive index with wavelength, we call it as dispersion. This is an important concept with respect to the properties of the transmission of the radiation. So, dispersion, what is a dispersion? So, dispersion is basically a complex phenomena. So, it is cannot be uniform for all types of matrix. So, what happens? The dispersion curves we obtain whenever you plot the energy of the electromagnetic radiation when it is passing through a given matter. So, given matter means you can assume a block of glass or a prism for most of the discussion that we are going to have here in this session. Okay. So, there are two types of dispersions. One is normal dispersion, in which there is a gradual increase in the refractive index with increasing frequency. Okay. So, the refractive index gradually changes and you can predict what happens if I take 1 centimeter block or 2 centimeter blocks, how much it will bend, where it will come out of the system, at what height or depth, etc. So, that is normal dispersion. Okay. Anomalous dispersion occurs at frequencies with sharp changes. Suddenly it will change the direction in the matrix. So, if you plot the energy changes versus the direction or the energy changes versus the thickness of the matter, then it must coincide with the natural harmonic frequency of some part of a molecule existing at that point. Okay. So, it may be a molecule, it may be an atom, or it may be an ion. So, leading to the absorption of the beam. I hope you have understood this slide. Now, in spectroscopy, dispersion curves are very important for us. You know why? Because most of the optical components appear as lenses, mirrors, etc. So, most suitable components for the manufacture of lenses are those in which refractive index should be high and it should be constant. So, this is the criteria that we normally infuse whenever I want to select a particular material, because I need lenses, I need mirrors, and I need several optical components in a spectrophotometer or in a spectrometer, whether it is spectrophotometer or infrared, near infrared, all are essentially the same. So, this results in which refractive index, it must be high, it must be constant. Why refractive index should be high? Because it will allow no distortion, okay, of the incident light. the incident light should not be distorted and it should be constant. It should not lose its properties, such as energy, frequency and this thing, that is also important for us. Well, then what do we want from lenses and mirrors? We want perfect transmission through the lens. Sometimes we want the lenses to give us a parallel beam of light, that is high school physics or second year PU physics. If you look up the transmission of light through the lenses etc., mirrors, you will come across those things. But at this point it suffices to say that what we want from a lens is a parallel beam of light, concentrated beam of light, sometimes focused beam of light, all those things we require, and for such purposes the refractive index should be high and it should be constant, another property. So, this results in reduced chromatic aberrations. That means, what is a chromatic aberration? A chromatic aberration is the distortion of the incoming light or incoming electromagnetic radiation through a matrix, that is chromatic aberration. There are several types of chromatic aberrations. Sometimes if you take a look through a lens like the specs etc., you look through one side, you will see things blurred. It is all very common experience. Sometimes they look blurred, sometimes they look distorted. You would have seen in the cars etc., the images appear bigger or very small. The longer distances do not appear equal long, they appear too long or too near. Most of the car mirrors show such properties, and sometimes they show bigger images. So, the chromatic aberration is part and parcel of every matrix that is transmitted, that allows radiation to pass through for transmission. That is what we are discussing now, the transmission of electromagnetic radiation. So, for the fabrication of prisms and refractive index, what we need is it should be large, but also highly frequency dependent. This is important. Okay. Now, we will discuss a little bit about the reflection of radiation. I think I have already referred to you, talked to you about the reflection of the radiation, is not it? So, we see our reflection in several mirrors etc., right from morning to evening, mirrors, toothbrushing, face decoration, getting ready and all those things, they are all plane mirrors. So, plane mirrors are not supposed to show you different picture of yourself across the mirror, otherwise the whole concept of mirroring is gone, is not it? So, it should show exactly as you are. Now, sometimes we also want reflection without any loss of incident radiant power. We want the mirror image should be as bright as I am as the brightness prevailing outside the mirror. Okay. So, the such mirrors, they can be concave or plane. Plane mirrors are usually what we normally use in our day to day life. Sometimes we use a curved mirror, something like this. If you consider this, it is convex. If you consider the mirror this side, then it is concave mirror. Okay. So, it does not mean that a mirror is always convex or concave, whichever way you use. No, one side is only mirroring, the other side is only reflecting. So, the concave mirror will have a non-reflecting material on the convex side, and convex mirror will have a non-reflecting mirror on the convex side. Okay. So, they are basically used as optical components in a spectrometer. Okay. So, concave mirrors normally reflect the radiation as well as they concentrate. That is one of the advantages of mirrors, because they do two jobs. One is reflection and another is the concentration. So, in cars etc., there are concave mirrors, because they want to show you long distances, what is coming at the back, maybe 10 feet, 15 feet, 100 feet etc., whenever he is trying to negotiate a curve. So, in cars etc., we need concave mirror, and sometimes we also need convex mirrors to show. Convex mirrors means they show the reflection in greater detail. If you must have seen in several pictures the heroes and heroines, they show bigger face and what not compared to the screen size. So, concave mirrors reflect the radiation as well as concentrate the reflected radiation at its focal point. Okay. When radiation crosses an interface between media differing in refractive index, reflective index, reflection always occurs. This you should understand. So, the radiation crosses an interface between two different media. We can always imagine the radiation passing through an air and then passing through a glass mirror or a glass block or a plastic block and then coming out. So, that is what we are talking about. So, when radiation crosses an interface between media differing in refractive index, reflection always occurs. So, for a beam entering an interface at right angles, the fraction reflected is given by this relationship, that is intensity of the radiation reflected to that of the intensity of the incident radiation is given by N2 minus N1 whole square divided by N2 plus N1 whole square. So, here I0 is the intensity of the incident beam and IR is the reflected intensity, and N1 and N2 are the refractive indexes of the two media. Okay. So, these two, this expression is assumes very important, because whenever we want to use a material, I have to know what is the refractive index of the material. So, refractive phenomena I can always show like this, that it is this is a block of glass and then radiation is coming like this, and then this is the perpendicular to the glass, and then it comes here, changes direction and then again comes out of the this thing. That means, if the changes were not there, if the glass was not there, it would have travelled like a straight line. Even though we say that it is wave electromagnetic radiation travels in waves etc., in simpler terms, for practical purposes we can think of it as passing through passing as a straight line, as I have told you in the torchlight. So, system, even in the torchlight system there is a glass, there is a media change from the bulb to the glass of the torch and then to the air outside. So, this is what happens most of the time, and then we will see this refraction phenomena in general like this. Okay. And I think we will look at the Snell's law and other things in our next class. So, thank you very much. We will continue our discussion on the transmission of electromagnetic radiation through other systems also, we will consider the interactions. Thank you very much.